Okay, so in this class, this module, we'll be discussing what is this? Click. Okay. Never mind. So what we'll be discussing is tension blobs, which are also called Pincus blobs, and this is from page 4 of so basically, I'll just start by reminding you what is the difference in behavior between a single chain, the conformation, and dilute solution, ideal chains versus real chains with excluded volume. Here, the extent, a measure of the extent of the chain, end-to-end vector, if you like, or RG, if you like, E goes as B. B is the bond length, and N number of monomers to the power half, which is called the ideal chain, and this shall be represented as R0. Whereas for real chains, the measure of the extent goes as B, bond length, N number of monomers in a chain to the power 3/5, and this shall be referred in the next half an hour as RF, where F stands for Flory, the extent for the Flory chain, where excluded volume interactions are being taken into account. This is the ideal chain R0, right? So when you have an ideal chain, so let's start with the discussion of the ideal chain, and we'll come to the Flory chain. Now, suppose you're applying. So this is the ideal chain conformation in general, a random walk, a perfect random walk, overlap. I mean, it's not self-supporting. It can overlap with each other. And now suppose you apply a force F to the two ends of the chain, and the chain has n monomers, as a consequence of which the chain will be extended, okay, by a small amount. You are not applying a huge chain so that it becomes perfectly straight. So each part of the different segments of the polymer chain still can take various large number of conformations. For this case, for the tension blob, or the so-called Pincus blob, we say that below a length scale of zeta f, f for force. In Rubinstein, by the way, this is also referred to as zeta t, t for tension, but here I have replaced it by f so that you don't get confused with the thermal blob. So zeta f, if you like. So below the length scale of zeta f, the polymer chain remains ideal, indistinguishable from ideal. And so basically the entire the stretch conformation is a sequence of so-called tension blobs. So only at length scales above zeta f can one decipher any change in conformation, and the free energy change is basically kBt per blob, which we have been using always. Okay, so basically then this becomes an elongated chain of tension blobs. So how many blobs are there and how many monomers are there? As in the past, we are saying GF monomers per tension blob, and the number of tension blobs is N by GF, because each blob has GF monomers. So total number of blobs is N by GF, and N by GF blobs are basically placed one after the other. Okay, so, and that's the length of the chain. So that's what is written here. Suppose the extent of the chain as a consequence of stretching in the direction of stretching is called Rx, and that is equal to the length scale of a tension blob, which is zeta f, into number of blobs, N by GF. And what is the length scale of zeta f? That is, it's basically within that you consider an ideal the GF monomers, and zeta f whole square equal to B square into GF, right? So that's what it is. So we are going to use these relations. Moreover, there are N by GF blobs, and each blob contributes kBt. That's the input, right? That's how we think of blobs. So dF, the change in free energy due to application of this external force, because of this external force, number of conformations have decreased, hence the free energy has decreased, has increased. The change in free energy is N by GF into KBT. But in doing this calculation, as in the past, we don't know a priori the values of GF, the number of monomers in a tension blob or a Pincus blob, number of and the length scale of. These are mental constructs for analysis. But what we do know, we can measure the extension due to the application of the force. Moreover, we know that force F has been applied, so, because you can apply an external force, right? So either you know that, or if some force has been applied, then you can measure the extension. These are the two things which can be yeah. So recording is going on, no problem. Sorry, I just wondered. So this relationship holds. The extension, the size of a blob whole square goes as b square by g to the power f. And now in this relation, Rx equal to extension size of a length scale of a tension blob into number of blobs. Here GF we are replacing, right, by using this expression. So basically GF equal to zeta f square by b square, and that's exactly what we are replacing in the denominator, as a consequence of which we get this, and b square by zeta f. What is the message? If we know what is the extent, and if we know how much is the extent after pulling, and if we know what is the size of the ideal Gaussian chain, nb square, then we know the size of the length scale of the tension blob. Zeta f equal to nb square by Rx, and by suitably substituting zeta f square, this relationship, if you like, we can know number of monomers in a tension blob, which is n square b square by Rx square. Length scale matches, right? Now, using this expression GF in the free energy, expression for the free energy. What is the free energy, or the change in free energy, the excess free energy? It's KBT by number of blobs. Now I'm replacing GF, this expression, and then we get the change in free energy goes as Rx square, extension square, the length of, it's not just it's not just change in extension, it's the length on of the chain on application of F, and divided by NB square. So the force is del F del Rx, and we get this expression, right? KBT into Rx. Now what is NB? NB square. That's essentially R0 whole square, if you remember, right? So replacing, basically replacing, you can find out F equal to KPT by zeta F, because this quantity is zeta F, right? So you can just look up the expression of zeta F here. So what is the message? So if you know the force being applied, then you know the length scale of zeta F. And if you know the length scale of zeta F, then you know number of monomers in a blob. Alternatively, if you know Rx, then also you can calculate the F. Yeah. So if you suppose you can measure the length of the stretched polymer, then you know how much force has been applied. And then you can again calculate all these GF and zeta F. On the other hand, if you know force that you're applying, and you have to of course know the total number of monomers in the chain, and of course you are assuming ideal chain conformation, then you know what is the value of Rx and so on and so forth. Right, so this is what will happen for a ideal chain. Now just comparing tension blobs for ideal versus real chains with excluded volume. So this relation zeta f, which goes as b into g to the power g to the power half, right, or rather gf to the power half for f for force, that is replaced by zeta f with real chains b into g to the power 3 by 5, and thereby you can write down the expression of gf in terms of zeta f. Now the other concept remains the same. Rx, the total extended length of the chain, is the zeta f for real chain into number of blobs. It's the length scale of a blob, tension blob, into number of blobs. Here you are replacing gf from this expression, and as a consequence Rx that you get becomes a different expression from here, right? For the real chain, of course, you're going to get a different expression. All that was different was here, the rest we are following all the same. So we get this expression, nb to the power 5 by 3 zeta f to the power 2 by 3. Right, but now for a Flory chain, we know that Rf goes as b into n to the power 3 by 5, and if you want to replace n suitably, then we can write Rx in terms of Rf as well and zeta f as well, right? So we can write this, right? And then after a bit more of a manipulation, what we get is zeta f, which we didn't know. What is the size of the blob in terms of the Flory radius Rf, and you can measure this quantity Rx, how much is the extension. So these are measurable quantities, and from that you are getting the value of zeta f, right? Okay, and then we were calculating free energies. So the free energy is again kBt into number of blobs, but gf so n by gf has some other expression. So I've written the ideal also in for comparison. So this basically comes from this relation, n by gf is Rx by zeta f, and that is exactly what you substitute here, right? So you're getting the change in free energy. So though I've written free energy, it should be ideally change in free energy, right? So that is because it was in an equilibrium f0. Now you've pulled it, so you have stretched the chain. Fewer number of conformations are available, so free energy is increased. So the change in free energy has been kBt Rx by Rf to the. This is what you get, right? Because you have just replaced the expression of this quantity. Okay, and then what you get is the force, which is del F del Rx, and that is, when you take a suitable derivative, it is Rx by Rf to the power 3 by 2, and then there's an extra Rf sitting here. Okay, so now compare with this. For the ideal case, you are getting F equal to Rx by R0 whole square, whereas here you are getting, of course, kBt is there in both cases. It is Rx by Rf to the power 3 by 2. Now, for the same value of extension, suppose you have stretched a ideal chain and you have stretched a real chain to the same length, so that the value of Rx is the same, then Rf is going to be more than R0, right? So it is going to be more. So this quantity, the F, is going to be lower than this value. So this was more compressed. You've reached the same value of Rx. So this is going to be so this is going to be lower in value, but the increase of force with Rx, this was a linear relationship, this is a 3/2 relationship. So if we plotted the force versus Rx, right, and this curve will start from R0 if you like, and this should actually start from RF, this blue line. So blue line is basically the blue line is supposed, this shouldn't start from here, it is basically RF going up till a certain value Rx, okay, and then slowly increasing. Then F will have a lower value for the ideal chain. So for the real chain will have a lower value than for the ideal chain, but the slope, the change, the increase, the rate of increase is higher for a real chain. So this is the basic message. Okay, then let me quickly go over to compression blobs, so which is the next idea. So that was the idea for the tension blobs, and now I shall go over to the compression blobs, and again I'm comparing ideal chains versus real chains, self-avoiding real chains, and compression blobs I'm referring as GC, the number of monomers in the chain. And okay, so compression blobs, they can come in two, so they can come in two flavors. You can compress blobs in a cylinder, right? So it's surrounded, so this is a polymer chain, and I have basically schematically drawn blobs, and since they're confined, they are forced to stretch out in this direction, and the maximum extent of a blob in the, so this is a cylinder of a diameter d, so it is confined in both directions. So suppose the axis of the cylinder is along z, then it is confined in both x and y directions, hence it's a biaxial compression. So when a polymer starts, it can basically do a random walk, it can do an ideal chain random walk, or it can do a self-avoiding chain random walk, whatever it can do, but the maximum extent in the x and y direction or radially outwards can be diameter d. So that basically sets out the size of a blob, and the entire chain is basically a collection of blobs lying along the axis. Okay, so d, the length scale, so in the length scale of the blob, the radius becomes the radius, the diameter of the tube. So d equal to b gc to the power half. So instead of zeta, which was always giving you the length scale of the blob, here we are using d. Okay, and again for real chains we are using d. The difference is this is b gc to the power half, this is gc to the power 3/5. What is the other idea? The other idea is how are the blobs arranged along the axis. And if you have an ideal chain, the extent along the axis of the cylinder can be called R parallel, and that is d, which is basically the size of the blob. Now these blobs can easily overlap if you have an ideal chain, right? Because so they can overlap because they can see through each other, and using the ideal chain statistics, you say that d is n gc to the power half. So these blobs can overlap, whereas in a self-avoiding chain you're not going to do that. You're going to say so this is gc to the power half, whereas for a self-avoiding chain the blobs can't overlap, and you say R parallel equal to d, the length scale of the blob, into number of blobs, which is n by gc. So they are all lined up one after the other, whereas here they are overlapping. The statistics along the axis is not changing, So in an ideal chain, it remains n by Gc to the power half. So Gc is d by b square, whereas here Gc has a different behavior, right? So basically you're using, here you're calculating Gc from this expression, here you're calculating Gc from this expression, and substituting the expression for Gc here, you know. So in the R parallel D, so here substituting this Gc here, and R parallel goes as b into the power half, but R parallel for the real chain goes proportional to n. So the extent of a polymer chain for a real for a real polymer chain with extruded volume along the cylinder is proportional to n. Of course, you have assumed that there is no because there is no, what is it called, confinement in this direction. If there is confinement that in this direction, in the z direction, there will be other effects, right? Because the blobs, blobs have to overlap and there will be more energy. So free energy for both remains, the expression remains the same, kBt and number of blobs, kBt into number of blobs. If you substitute the expression for G, free energy goes as Rf by d to the power 5 by 3. This is the Fourier extent, Rf equal to b n to the power 3 by 5, whereas if you substitute G here, it goes as kBt R0 by d whole square. So that's the difference. Okay, so for an ideal chain, this is how it would look, that the blobs are overlapping, because an R parallel goes as b into the power half, but for a real chain, R parallel goes as n and the blobs can't overlap. Right? So they are basically lined up along the axis of the cylinder. So that's the basic message, right? Has been a lot of ideas. Just to tell you, compression blobs, Gc depended on d, diameter of the tube, right? For the ideal chain as a whole square, and Gc depended upon the diameter of the tube to the power 5 by 3, and that's how you get your compression blob, and you can get the length scale. The length scale of the blob is of course d. In tension blobs, the blob dependent, the length scale of the blob dependent on F, the externally applied force for the ideal chain, right? Like this expression. And if you got by chance this size of the blob, the length scale of the blob, then you know how many number of monomers there are in the blob by this relationship. This is for ideal chain. You can also express zeta f in terms of the extent of the chain. So that's the idea of tension blobs. And for the real chain, zeta f had a different dependence. It is Rf to the power 5 by 2, the Flory length scale, the entire chain, and extended. You know, in a tension blob, the blob is essentially, the message is depending upon the strength of the force, or if you like, the extension. And of course, these two are related, right? And they are related by F equal to kBt by Rf, Rx by Rf to the power 3 by 2. The blob, what is the message? The number of monomers in a blob, the length scale of the blob is basically dependent upon Rx extent, and of course the Flory length scale, right? And if you know these two, then you can find F. I mean Rx, you can find F, or if you know F, you can find Rx, and then you can use these relations. For the correlation blob, just to remind you, the number of monomers in the blob and the length scale of the blob depended on the concentration of the monomers. That's the case, the semi-dilute case. As you increase number of monomers, the size of the blob decrease, the number of monomers in the blob decrease. So that was dependent on the concentration. And the first topic was the thermal blob, and it dependent upon the bond length as well as the excluded volume parameter V, right, which also incorporates, by the way, KBT and the potential. By the way, even correlation blob has had expressions of V in the expression for G and zeta, right? So basically this is a summary, and just as a quick discussion, uniaxial compression. So uniaxial compression is basically compression between plates. For the ideal chain, so now you have a chain, you have a polymer chain between two plates. But you know, since an ideal chains can easily overlap, there's no energy cost for overlap. As a consequence, its dimension, its extent, in of course, in the if this is the plane, and suppose the z direction is perpendicular to the two planes within which it is confined, there in that direction it's confined, but the radial extent in the plane remains unchanged for the ideal chain. On the other hand, for a real chain, d would give d being the distance between the two parallel plates. You would basically have a size of the blob of that in that dimension. So instead of zeta, you would have d, the distance that would be the radius of the diameter of the blob. And what you would have for a real chain, the self-avoiding random walk of blobs. And self-avoiding random walk of blobs in 2D has a Flory exponent of 3 to the power 4. And then what you would have is the extent in 2D is basically d, which is like now is equivalent to saying that b is to the bond length. That's the length scale of the blob, and number of blobs to the power Flory exponent in 2D, which is 3 by 4, which can be compared that if you have a normal polymer chain in 2D, in the ideal 2D case, you would have the end-to-end vector distribution or a magnitude of the extent of the polymer chain as b n to the power 3 by 4. Instead, you have d, number of blobs to the power 3 by 4, and g, if you calculate g from this expression, d goes as b to the power g to the power 3 by 5, because at that length scale nothing is being altered below the blob length scale. So from this expression, if you get the value of g and substitute it here, and I've substituted it here, what you get is essentially r parallel goes as n to the power 3 by 4, which is what you would get. That's what you would get in if you had a polymer chain just in 2D, the theoretical construct, but here it is confined, and again you are getting r parallel goes as n to the power 3 by 4, which is like close to something like the 2D self-avoiding random walk. So this is how you get 3 to the power 4, and b by d to the power 1 by 4, which you get just by substituting, and there's a b sitting here, right? So what is the message? If you have d decreasing, so the distance between the two plates come closer, then the polymer is going to spread out. But how is it going to spread out? d to the power 1 by 4, right? So that's how it's done. So that's all that I had to say in terms of blobs. I don't have much anyway, but at least I hope you got an idea about the various kinds of blobs. I didn't talk about adsorption blobs, but if and when you need it, you can read it up. So there actually the blob size might increase as you go away from. So that's all. With that, let me end this section